We talk about the floating base dynamics, and now we will have a look into that to see some specific peculiar properties of this on the sparsity of this dynamic equation whenever you reparameterize the general coordinates in centroidal coordinates. So we saw that we have these couplings from the joint variables, and to be able to do a planning only on the underactuated variables without completely taking care of the joint coordinates, we need to have to remove these couplings. And a way to do that is redefining the way we parameterize the base generalized velocities. In particular, if we reparameterize the base generalized velocity into COM velocity, we will see that this coupling will disappear. First, why? This also useful comes into our direction because we want to control the central mass because of stability reasons instead of the base. And in particular, if you think about a central robot, wherever you have an arm on top, the floating base frame will be normally in the middle of the trunk. Then you have the arm, and this will shift the central mass forward. And in the case of IQ, it was shifting even 10 centimeters forward. And what it matters for stability is the central mass, not the base position. So this parameterization it's meaningful, and and this change of state variables, as we said, will have the nice effect of diagonalizing and completely decoupling the underactuated part, diagonalizing the inertia matrix, and completely decoupling the underactuated part from the actuated part. And instead it transforms we are talking about is to use the central mass velocity instead of the base velocity. And as a first step, we consider the angular velocity of the base unchanged. And in this case, this means that the frame we use to represent the floating base will no longer be the base frame, but will become the COM frame. Let's say a frame G that it's located with the origin in the central mass, and it's aligned with B. So this is this drawing is wrong. It should be aligned with B. In this case, the base velocity we saw that maps into COM velocity, considering the fact that the central mass velocity, how does it look like? As we did for the foot, we have the component due to the base, so the central mass will move as the base, plus we'll have the component due to the fact that an angular motion of the base will create a linear velocity on the central mass. So cross x, the vector that goes from the base to the central mass. Okay, and this, as we saw, it can be mapped with a skew symmetry matrix. Plus, we have this component here. What is this component due to? The central mass, we saw that depends on the position of the links. So if I move the links, all the legs to here, where does the central mass go? More on the left, shift left. If I move on the right, the center of mass goes on the right, and the same also for the velocity of center of mass. So if I move the links quickly like that, also the velocity of the center of mass, so it will change. So if we have Jacobian, let's say, that will affect. It will depend on the joints, and will affect the velocity of the center of mass. Yeah, I will call the JCOM. It will affect the location of the center of mass in the base frame. That's why I wrote JDCOM to distinguish from JCOM, which is the Jacobian that it's all this JCOM in essence. It's the links the COM velocity from to all the joints, even the base one. The omega doesn't change, so we have an identity matrix here, and also the set of joint velocities. Sorry, this is Q dot. Also here, it is not changing. So we have a transformation matrix that maps a certain generalized set of generalized coordinates that consider the floating base representation with the base link to another set of generalized coordinates that use for representation of the floating base a frame that is attached to the center of mass. And of course, this QB dot is not the QB lowercase that we use to represent the base velocity. And we know that this is the transformation that does the mapping. Now, if we want to define this transformation, if we look at the acceleration, vector of generalized accelerations. So if you have this transformation going to be dot, when we do the acceleration, we will have the derivative of the derivative of QB dot plus derivative of the transformation itself times QB dot. And if we replace this here, we can do this transformation is invertible. Okay. So there's a lot missing there. I will correct. I will continuously update the slide whenever I spot the typos, and I will upload the latest one. Keep downloading the latest slide because this is something I see now. So if we do we express in QB dot and QB dot, we get these expressions, and we know that if the end effector velocities is invariant if we change the frame, we represent a floating base. So in essence, we have the foot, for example, velocity is equal to the Jacobian that is built using this. This is not mapping to the base frame. It's a Jacobian built using this new frame. So we will have different JB component. So this term will be different. And this is equal to the one using the G. So if we replace QG with this, then we can find a relationship for the Jacobian. This is follows, and if we do the transpose, we get this. So J transpose is equal to tau as we said, the Jacobian is different because we changed the floating base frame. The torque is invariant, so there's the same vector of torques. And if we do this replacing of all these elements into the dynamics, the original dynamics that is written on the base frame, we perform the change of variables. Now to use the notation, we call the transformation TDG into we rephrase to call it as T, and this is how does it look like? So in essence, we start from the original floating base equation. As this is the mass matrix original. As I said, this is not the MB, but it's just the mass matrix using the floating base in the base frame. So the original was like this. And these are the contact forces. So if we replace this with this relationship to get the mapping, we get this. And if we multiply by T to the minus transpose, then this element goes away, and we get this expression. So we get a new matrix, Mg, which is the joint space inertia matrix using the floating base, the COM frame. Why we left multiply by these elements? Because we want to show up the same structure as here. So we have now the contact forces that are mapping into the equation through the Jacobian that is Jg, and then we have the same vector of torques. We have a new gravity vector that is called Gg, a new Coriolis matrix that is called Cg, and a new inertia metric that is Mg. Sorry, this is the accelerations missing here, Qg dot dot. And so this is the dynamics using the COMS floating base. And if we inspect, this is a paper of Ott 2011, the structure of this inertia matrix, we see that it's block diagonal. But so we see that the central mass acceleration is not is independent from the joint acceleration. So we eliminated the coupling coming from the joints, but only for the central mass. So we still have some couplings on the angular part. So here you see that oh, this is 3 times n plus 3. Sorry, n plus 3. So this is 3 times 3. This is 3 times n plus 3. Yes. And this is n plus 3 times 3. And this is which is like n plus 3 n plus 3. So let's do now a little detour recalling some centroidal quantities that are useful for the next development, and that will be useful to achieve a full diagonalization of the inertia matrix. First, the total momentum. Let's define the total momentum, that if you use Euclidean algebra, where you need to express it reference point and frames. So if we express the total momentum in the world frame, the inertial frame is the sum of all the linear angular momenta for each rigid body. Each of them expressed with the origin of the frame W. Since we are using so we need the total momentum will have a linear part and an angular part. The angular part is the one that needs a point to compute the angular momentum, and as a point we use the origin of the frame, while the axis of the frame can be used to represent the vectorial quantity themselves, so both the linear and the angular one. So ideally we would just need one point, but to get numbers we need also the axis to get the coordinates of the numbers that represent this entity. So the linear forces, we will see they affect both the linear and angular momentum, and the moments affect only the angular momentum. And they, to be summed, they needs to be projected in the same frame. So the frame, as I said, the W conveys two information. The origin, as I said, is the point about which compute the angular momentum. The axis are the vectors where the frame where we express these vectors. And but there is no we are not forced to use the word frame. We can express the total momentum of the system in another frame. And if we select the frame G attached to the central mass, align with VW this time, so before we align with B, but people in the robotic community like to attach a frame to the central mass and align with the inertial frame. Then we are talking about, instead of the total momentum is called centroidal momentum. And the centroidal momentum is as the linear part, which is the thing. Since the total momentum is the sum of the contribution for all the links, as likewise, since the contribution from all the central mass is the contribution from the links in terms it's a weighted contribution of all the links. We have that the linear momentum of all the robot is due to the total mass times the velocity of the central mass, and the angular part is the angular momentum as well referred to the central mass frame origin. And as well is the sum of contribution of the angular momentum of all the links. So this is the we can distinguish two components. So the angular momentum of a link due to the with respect to the central mass of the link, plus the angular momentum of the central mass of the link due to the velocity of the linear velocity of the link that creates a moment with respect to the central mass. So if it's not clear, and I think it's not. We have the frame G. So we have one link here with this little center of mass. So this guy will have velocity. And also angular velocity. And we will have a mass and an inertia. So the contribution is to compute the contribution due to the rotation around the central mass itself, which is Li omega I, and plus the rotation around of this the angular momentum of the velocity of the central mass of the link with respect to the G. So it's if we go there, x ci minus x c1. This is x1. Cross product the velocity. Of course, this velocity is the Wolfram, so we need to be consistent. And summing all this, we get the total angular momentum. And so what happens? As I said, that this if we are considering as pole to compute the angular momentum, not the central mass origin, but another point external, then we get just we add this component to the kg. So this is a kg, and we have the position of the central mass times the angular momentum of the central mass, and we can refer everything to a frame external solid. So this here it was like this. It was referred to this frame, so it referred to an external frame W. Yeah, this. So now that we map everything into COM, we get the kg, and we have the velocity of the central mass, and we have the total mass of the robot. So linear velocity still is the same in terms of affecting the linear momentum, while the angular momentum, it's whatever we computed, kg plus the contribution due to the fact that we are expressing a sport to compute the momentum here and not here, so we have the velocity of the center of mass times the mass of the robot, total mass, and axiom first product is. Okay. So this in case you need to compute the momentum in a frame that is external. Then if we do that, we see that appears a convex term. So this is kW. So kW person work frame. And we see that this term is a cross product between the central mass position and the central mass velocity. So it's something that is non-convex if you do optimization on kg, because you have a cross product which is a nonlinear operator of two decision variables. And one way of fixing this, this is the recent thesis of Onkai Dai, is to, for example, we can look at this as a linear function, because this term becomes linear if you fix one of the two variables. And so if you put an upper bound either on this or on this, you can make the problem linear again or convex. So this is a detail for optimization. Now let's talk about the locked velocity, locked spatial velocity, because we will need this. It's for a system of bodies, the locked velocity. Let's think a system of particles moving around. And the locked velocity is the velocity, the base link, like a single rigid body with all the links. Sorry, this is not the base link. It's just a single rigid body with all the link welded, all the link fixed, should move to get the same momentum as you consider the link moving. So in essence, we compute the total momentum considering the contribution of the base and of the joints. So the joints will affect the total momentum with their velocities, while the base velocity will affect the total momentum, let's say, as well with the MB matrix. We saw this before. And we say that we want to find an average, a locked velocity that is like a rigid body with the same inertia, that is the composite rigid body inertia of the robot as considered as a rigid body, that produces the same momentum as if the joint don't exist. So this is the way you compute this. It's a 6D vector with linear and angular velocity, and it's called locked spatial velocity. While the average spatial velocity that is introduced by Orin in his paper on Centroidal Momentum matrix, it's related to the locked velocity with a coordinate transform, which is this is a spatial coordinate transform that maps a spatial velocity from a base frame to the central mass frame. So this is a relationship between these two quantities, and we call this average spatial velocity. So it's almost the same, just mapped in another frame. And we are getting there because the frame we are considering is we are interested in this development is the human frame. Additionally, in the humanoid literature, is common to define as a function of spatial momentum in the G frame and inertia. And this is you remember the component, the 6x6 component of the big MG matrix we diagonalize. If we do this, in essence, this development, you can get an expression for the average velocity as function of the base velocity and of the joint velocity. Okay? This is, you want to go through this? We can do that. This is the spatial momentum that can be computed with computing the it's coming from the spatial momentum in G. It's coordinate transform the spatial momentum in the base frame with the force transform. So in spatial algebra, this is transformation to map branch. So this is a branch, a 60 vector with the forces and moments into another branch in another frame, and it's different from the one that we use without the star. That is to map twist. So spatial velocity in a frame in another frame. So this branch. It's obtained with this is the centroidal momentum matrix that we saw before from the joint coupling and the spatial inertia, and this is the full plus 6 generalized velocity vector. Then we wrote that the average velocity is it's the spatial inertia computed using the central mass frame times hg, which is this. And if we split these two, because we know that this is q base dot and qj dot, we get j this doesn't work anymore. Continue with that. Hope that you will see. And j minus 1 x b. Okay. And if you look at this, if you consider the how this MBG matrix is computed, it's like a transformation of the spatial inertia expressed in the floating base, and you left and right multiply for the force transform and the motion transform. This is the things like that. So if we collect, so this is -1. If we collect yeah, so we replace this term here, and we see that this Bg GB, there's an error. So this goes away with this goes away with this, and we remain with this term. So we have QB dot plus a term that is this one. Okay, so we have two contributions to the average spatial velocity, one due to the joint and one due to the base velocity. We can prove that these two are the same. It's possible to go back here, so we close the loop with the locked velocity, and classical mechanics researchers are happy, and if you analyze this relationship closer, we know that this matrix it's a diagonal matrix, because it's the in essence, if you express everything, the tensor of inertia in the spatial inertia in the center of mass, it becomes diagonal, and we have that these are all the contributions from the links that we saw before, and this is the total mass of the robot, which is the sum of all the links, and that's because we said that the centroidal momentum is the sum of the spatial inertia times the spatial velocity of all the links, and therefore we can say that the angular part of this spatial so this spatial average velocity is nothing else that the linear velocity of the center of mass and a term that we call average angular velocity. That is the angular velocity, as we said before, not that the system would have if you assume all the joints are fixed, that produce the same angular momentum as they are not fixed. It's an abuse of term calling angular velocity, because we don't have, this is not attached to any frame. It's just while the angular velocity should be representing the velocity rotation of a single frame, and for this reason we cannot integrate this angular velocity. So, for example, it's impossible to knowing this average angular velocity get the orientation of the robot, because we have the joint contribution, and the joint contribution will change the inertia of the robot, and due to the conservation of angular momentum, think about a cat that is falling and is reorienting its joint moving his joint to reorient himself. Ideally, the angular velocity it should not change, because you have no external forces, so the conservation of momentum, it says that if there are no external forces, the angular momentum should remain constant, but the orientation changes because of this motion of the joints. So the motion of the joint will change this element, and you will have a change in the orientation. So if we use this angular velocity, average angular velocity to define unique parameterization, so we change the base velocity to CM velocity and the angular velocity of the base into average angular velocity. We find a new transformation matrix tau b j bar that will have we will have this shape. So we need to here we put the term xbj, and that will be like that. So this part will be the term xbj, and the other part will be the term we computed. And this way we have the average spatial velocity here, and here the base spatial velocity. And using this transformation, we have so do you know this that xbj, it looks like this. You got this? We kind of saw before. Whenever you transform a velocity, partial velocity from one frame to another, you have depending the position and orientation of the ending frame, you have this expression. Since the G frame, should be aligned, we have an identity matrix, there is an error here, and this is the segment that goes from the base frame to the CM frame. And using this parameterization, if we replace, we find a new dynamic equation in the new variables that are the QG bar ones, and the new matrix, a new correlates, and a new guarantee matrix. And if we analyze this new inertia matrix, we see that it's completely diagonal. So all the couplings are removed from the joint, even for the diagonal, for the angular part, and we can decouple the we can decouple this underactuated equation from the actuated equation. So all the floating waves acceleration, both angular and linear, are independent from the joint acceleration. The gravity vector becomes like a constant, so you will have this form. So it's simplified, and if you have this, you select C such that this is skew symmetric, you will have also Coriolis matrix that is 0 in first 3 rows, and only has influence on this. And we will see that this is on the angular part is the influence of the joint in the inertia of in the tensor of inertia of the whole system, because this is dependent. Because if I have my joints extended like this, how is the tensor of inertia of me as a rigid body? It's bigger or lower than if I keep the joint like this? It's bigger because I have the inertia more, let's say we are considering an axis of rotation vertical, I have a bigger inertia in this case than in this case. This is why dancers, when they turn the pivot around the foot, to speed up, they close the hands. And so we are able to consider these two equations decoupled, completely decoupled. And if we look to the JEC, so to the Jacobian part that we need to redefine. This looks like this. This is you remember we saw this for the base, the JB, the JCB. JCB was the identity matrix, or depending if we so it was the identity matrix and the position of the foot minus the position of the base. And now we do since you are changing the frame to the COM frame, we are doing the position of the foot minus the position of the center of mass. And if we rewrite this down, so we have the mass, total mass, times the acceleration of the center of mass. Then you have the gravity, and then we have JCB using the center of mass frame. It looks like this. So it's something, if you multiply by the forces doing this, it's like doing the sum of Fi. And for the angular part, we get the Lg times the spatial, the average angular velocity, plus some term coming from the Coriolis matrix, plus no gravity effect, because we completely remove that, 0 here as well from the torques, and the angular part from the Jacobian, which is again a sum of xfi minus xcom cross, this is now matrix fi, and you can see this as xfi minus xcom cross product fi, and these are the Newton-Euler equations. The Newton equation, the linear part, and the Euler equation in the angular part. So yeah, this term we will see it's due to the to the rotation of the moving frame. So the fact is that this as we said, this is a Newton-Euler equation. Consider the system as a whole, but simplified as a single rigid body. But this rigid body will have an inertia that is variable due to the joint position. How we place the joint position, and for this reason, these equations are called Centroidal Dynamics, and we see that this Lg, sorry, I changed the equation, is Lg, is joint dependent, and its derivative in time is non-zero. And yeah, then next lecture I will talk a little bit more how to map the Newton-Euler equation in different frames, because there's a lot of confusion on this topic. Now we could quickly look at the lab, which is lab 3. Now I changed the name. Originally it was lab 4, and then I moved into renamed to lab 3. And to see that whatever we said was true. I mean that the transformation diagonalize the mass matrix. So if this time, I don't know guys, you're a bit beyond. We can look at this together, or what do you prefer?
If you want, we can look it together very quickly. Yeah, for us to get an idea.
Do you have any other question? Let's see. So the spider. Clone, and we will have to do because I changed this. Cool. Okay. See exactly this one. So in this case we somebody has a mouse here? No. Sorry. In this case we use Pinocchio to load the robot, the IQ robot. This way, it's a very practical way to use example robot data package to load the robot model, create a data structure, and then we set an array of velocities to be 0, and of position we can go to the default position, which is the Q0. It's usually, in the case of IQ, like this configuration. With the joint in this configuration. And with the joint in this configuration, we can compute the 4 kinematics and update the frames, compute the mass matrix, the bias terms, and the gravity terms. And the first exercise to do was to compute the central mass. So in this case, we have a native Pinocchio function to check with that computes the central mass, and we have our algorithm that in essence we take the inertia of the link, we sum it to the incrementally to compute the robot mass, and then we take the position of the link with respect to the in this case to the base frame, and we do a rotation matrix to the word, and to map this link to the word frame, and we add also the translation of the base frame, and sorry, this is the position in the word frame of the link, Yeah. Okay. So this is the this is the position of central mass of the link in the link frame. Then you need to rotate toward this vector and add the position of the link frame in the work coordinate. So we got the position of the central mass of the link in work coordinate, and we can multiply for the mass each of these vector, and then divide by the mass of the robot, and then we get the central mass that is giving the same result as the position of the central mass from the native function of Pinocchio. Now, if we compute the kinetic energy, again, we need to set some velocity, because we need some velocity for the kinetic energy, and we can compare with the Pinocchio native function, showing that Q transpose times M times Q is giving the same result. And there is no difference between the two values of the kinetic energy. If the third assignment was to build a transformation matrix TBG. So for this we need the position of the base in work coordinate. We need to compute the centroidal quantities, centroidal momentum, and centroidal inertia. That is spatial inertia. This is what we call MVG. Then we initialize the transformation. This is the XVG transformation, which is a motion transform from frame B to frame G. We also need to compute the force transform, which is what we call the X star VG, which is related to the motion transform this way. I didn't tell you this is something spatial algebra. It's very common, and so we just do the inverse transpose of the motion one. Then we need to get what we call the MVJ, which in Pinocchio is called FB, or even no Pinocchio. Yeah, I should uniform the rotation. Yeah, and then we compute the term. You remember that to compute the average spatial velocity, the term that we multiply for the joint velocities that we set in TBJ. Remember was something like XBG something like this. This is rho average and QJ dot. And this is QB QJ dot. So this is we can build up this transformation here, and if we left and right multiply for the mass matrix, matrix, and G was the B, remember, was the BG minus 1. Remember the was that anyway was the yeah, I think it was like that. So if we compute that, we print we see that the matrix is completely diagonal, while before was print M, it was like not diagonal at all. Next exercise was to just check the gravity vector. And you see that is 0, 0, G, and G, sorry, 0, 0, 0, 0, 0, all zeros apart from the three elements that are the gravity vector in the warfare. Okay, so to summarize, today we introduce the floating-based robot as the naked robots as a special class of floating-based robot. We described how to compute the dynamics for floating-based robots and what are the peculiarity of these dynamics. We saw that we have different way of modeling the floating-based robot using minimal coordinate approach or excess coordinate approach, and in this second case we will have problem due to the parameterization of the orientation that will make such that our configuration vector is as a dimension that is different from the generalized velocity vector. Then we kind of get an intuition that these two equations could be the underactuated one describing motion, the floating base part, and the actuated part, one describing the dynamics of the joints, could be decoupled if we eliminate the coupling term at the inertia level. And for this, we found that if we exploit the central mass velocity instead of the base velocity, we could achieve a certain degree of diagonalization in the mass matrix at the linear level. And but if we use the average velocity instead of the angular velocity of the base, we could achieve the full diagonalization. And for this reason, we can work out we can decouple the underactuated part that now it's called Centroidal Dynamics from the actuated dynamics. And we analyzing how does the Centroidal Dynamics looks like, we created a link to the Newton-Euler equations that describe the motion in the linear angular motion of a rigid body, saying that we can consider as the mass of this rigid body the total mass of the robot, and as the tension of inertia of this rigid body the aggregated inertia of all the joints of the robot in a certain configuration. Okay, if you have any question, let me know. Otherwise we close the recording.